Okay, we are live. Welcome to another live discussion on the Assumptions of Physics program. Today we are going to be discussing essentially all problems connected to units, um, definition of differentials and how this should work in differential geometry or in differential topology and all of these. So okay, so that's there. That's there. And please, Julius and Logan, interrupt me if there is anything that is not clear so that we make this as more useful as possible. So, uh, the I think I'm gonna share my tablet so that I have something that people can look at and that I can draw on. So, start share screen, specific app, one app, and it's going to be this one. Okay, so we have it, and we are good. Okay, so there are multiple problems that are connected. One is just the definition of what is a unit and how they work in general. And it's one of those things that seems simple at the beginning, but then it's horribly complicated. And if you ever wonder why we don't have computer programs that just do automatically the unit conversion, it's basically you can't because units are a mess. Then there is the association of units to coordinates of a manifold. So you have manifolds and coordinate and units. And already here there is a problem in the sense that we restrict ourselves to manifolds. We don't have a general treatment because we need to understand units in function spaces as well. And function spaces are not manifolds because they're infinite dimensional. And so we need a solution that not only work for manifolds, but also work for sort of all the spaces that we need in physics. So problem is compounded. Then you have the problem of defining differentiability. And there is an abstract thing that you need to define, because in some sense you have to have a notion of differentiability, differentials, derivative and all that it's unit independent. But then you also need to understand that when you put units, what is it that you are doing, and so there is a relationship between differentiability and units that needs to be understood, and this is one of the problems that you have in differentiable calculus, that it's not done so well. And of course, something that I thought I should say if forgot. Oh yes, this basically you don't have geometry. So this has to be done in a way that that works for manifolds that don't have a geometry. So, for example, if you take the space of all possible blood work results, that's a manifold, but it has no geometric structure. There is no notion of distance between two different blood works. There is no notion of areas or volumes of blood work. Everything is done on coordinates, and you can change units because you can change how you specify things. You could specify these in densities and whatever. Like you can change your units and still get something. And so all of this has to work on something that has no geometry. Then you have, of course, the symplectic geometry. And this is a little bit boring. I don't think there is much to do once you have solved the differentiable part. The symplectic geometry is basically already done. But instead, when you have Riemannian geometry, so you have a notion of distance, I'm not going to be able to spell it correctly. No, there's an E, Rimani, and there you go. Geometry. Uh, that there is something there that happens that is new because you can go from covariant components to contravariant components, which means the units are changing. You can define units on vectors because now vectors are going to have a norm, and that norm can be associated with a unit, which is not something that you can do in symplectic geometry without a geometry. So there are things that are new for units and dimension, all of that remaining geometry that you don't have before, and also all of that needs to be figured out. Okay? Okay, so if this is a general picture, let's go and drill down in any of these pieces and see what we get. So for the notion of units, so let's make this example. So suppose that you have phase space, you have a position, you have momentum, and let's say that I have a singleton, I have one point, and let's call this A, and then you have 2 points, right? So effectively, units in general are there because we want to describe sizes of sets. So if you're just counting points, then you can just say that A is going to be 1 because it only has 1 point, and B is going to be 2 because it only has 2 points. And this is very easy. You're just using the counting measure, you take the sets, you look at the elements that you have. Now, though, suppose that you have a line like this, let's call this C, and let's call this D, okay? If we use the same measure, then you would say that the size of C is equal infinite, and the size of D is equal infinite, and that's not used at all because you want to be able to say that D is longer than C. So you don't use a counting measure. What you're going to use, you're going to use the distance. So you're going to be able to say, you're going to want to say that C is 1 meter, D is, I don't know, 1.5 meters, right? And so you're counting things in a different way. And so let's call this something else. Let's call this a measure in meters of C and a measure in meter on D. And of course we could have different measure. You could have a measure in a centimeter, and this measure in centimeter would give you 100. Now, you could ask, where is the unit? You could say, oh, the unit is the measure that I'm picking, and now this is just a number, which does not have a unit, it's just a real number. Or you could set it up in something else, saying that the measure has to give you a real number plus another object, which is the unit. I have no idea, but there is this sense that I want to be able to take the size of C and say that I have a size, and I have to pick a unit to quantify the size, because if I just use points, I just say nonsense. It's just everything is infinite. Now, the same thing you're going to have for P. So if I have E, right? I want to say that there is going to be a measure in units of linear momentum, which I forget what they are. What is it? I don't remember. Let's call them P. So that's a units of P, whatever those things are. And so you say, okay, E is I don't know, it's going to be 1 P, whatever that is. Good. Now you see that there is a problem, because if I want to say, okay, well, C is a set and E is a set, and so I want to ask what is the size of C in units of momentum, and this is not defined. Okay? The same thing if I want to say what is the size in meter of E. Well, this is not defined. This is just nonsense. So what needs to happen is that these measures are only defined on some sets and not others. Which sets are going to be the realm of applicability of one measure or the others? How does this domain work? I have absolutely no idea, but it's clear that there has to be something like this. So there is no sense that C is bigger or smaller than E. There's no such thing. But then you can take a square, F, and now this will also have a new measure. It's going to be a measure of areas of phase space. Let's take them in units of H. And we take F and we say, aha, this is, 0.8 in that unit. Now, on this measure, I can ask what is the measure in H of C. It's 0. And I can also say that this is the same in units of H of E. Right? So you have this funny structure that A and B are comparable. A and C are comparable as well because A is measure 0 with respect to C and C is measure infinite with respect to A. But A and C are not comparable even if E and C, these two, are not comparable, even though A is comparable to E and E is comparable to F, and A, so you can say that A is finer than E, and it's finer than F, and you can say that A is finer than C, and C is finer than F, but you can't say that C is finer than E. You can't say this, and you can't say that C is coarser than E either. These two things are not comparable. So what it seems to me that it needs to happen is that I can imagine to have all these sets and put them in, let's say, a structure, let's call it L, right? This thing is going to be basically a subset, let's put it like this, a subset of R squared, and probably this is going to be a sigma algebra, because these are the sets that make sense physically, that we can talk about what they are. And I will have an ordering on L, which is this thing that tells me which set can I say that is smaller than the other. And it's a partial order because some sets are not at all comparable. And in some sense, this big L will be a lattice. Will have a top which is the full R square. You have the bottom that is the empty set, and then you have all the sets that are let's say countably many points. Let's say finitely many points. And then you're going to have the sets that are ranges of position, so finite ranges of position. Well, let's just say Q because this is not really. So these are the ranges, finite ranges of position, and these are finite ranges of momentum, and let's say that these are finite ranges of areas. And then, of course, you're going to have the infinite somewhere around. So these are not all the sets, right? But these are always coarser than the points. The ranges of P are always coarser than the points, and so on. And in these classes, it's where you can define the measure property, where the measures of the units of momentum will give you a finite number. Same thing for here, same thing for here, and same thing for here. Here I'll be using the counting measure. And the point should be that whenever I pick a measure and I pick some type of unit U, I will have a particular set, right? Let's call that U as well. That is going to be measure one. So I picked the set U as a unit, and I say, aha, that's my unit. That's that I want to call it one. And then there are going to be things that are comparable. So you to U, right? So you're going to have some kind of sigma U that is all the sets that are comparable to U in a finite way, let's say finitely comparable. And these are basically the ones that are commensurate, basically the ones that are the same physical dimension. Because I can only compare in a finite way things that are of the same physical dimension. And then I will need to have that if mu of A is less or equal to mu u on B, this is going to be if and only if A is finer than B. So the measure has to respect this structure that I had, right? And so the units should be effectively equivalence classes of this big lattice based on the final comparability of one statement to the other. So this is kind of how it should be. Now, how to get all the axiom to make this work, I started doing, and I don't know, I don't think we should go in the details, but I have a bunch of stuff that is done essentially recycling by some work done by De Finetti and other people that wanted to essentially rederive probability measures based on the idea that you have statements and you can say, oh, I think this statement is more likely than the other statement. And then from these, basically would be this, with some, sort of a consistency condition, and you can recover the fact that you have a probability measure. This is basically very similar, except that we're doing it at multiple different levels, because we don't have one measure. We have different measures depending on which unit you pick, and then different sizes that are not, the different elements that are not comparable. The thing that we were never able to understand was what are necessary and sufficient conditions such that these classes exist. Essentially, what are the can I say, what are the assumptions that you need, that you require to be able to define physical dimensions? That's basically what it is. Okay, so this is the sort of most fundamental level of this, and it basically needs to go from statements, which are these sets, to measures. And once you know that you can do measures, you can forget about all the other things, and we can go at the second level, which is manifold and units. Okay, any question so far? Okay, good. I don't know if from the chat is a question, but okay. I will stop if I see a question popping up. Okay, so that's the thing for just units, and now we want to talk really about manifolds. Oh, I should say other things first about units as well. So there is this. So there is also operations of units, and those we are really not even going to touch today. But the idea is that if I have something that is a physical dimension of distance, right, and I have something that is a physical dimension of angle, right, and I multiply them, can I tell you what is going to be the unit that comes out of that? And the answer that people were saying, oh yeah, well, distance times an angle, the angle a pure number, so you get a distance. No, you can't. So to be able to know what happens to units when you have a function and you're doing something with units, you need to understand the physics problem and you understand how the end is related to the beginning. So you can't really just formalize the calculus on units and physical dimension in a way that it's simple, that you think that it works. There are also units like decibels, entropy, and so on. There are ratios, and they work completely differently from the standard units that you would think. There are units of temperature that have an absolute zero. Therefore, the transformation rules depends on whether you are changing absolute temperature or relative temperature. So if I give you, 1 Kelvin, convert into Celsius, I didn't give you enough information, because if this is a delta temperature, you have a 1 Celsius, but if it's an absolute temperature, then you would have, what is it, 270, whatever is the thing that I don't remember right now, 274 maybe, something like that. Right, so there are all these issues. I'm not going to even talk about those, but just to tell you, units are complicated, and whatever you think they are, it's usually more complicated. Okay, so that's one thing. Now for manifold, you want to say that you have a space X, right? And you do want to say that the points really don't have units themselves. It's the coordinates that have units. So if I have a physical space and I have a position, the position doesn't have a unit. What happens is that at some point you put a coordinate system on this thing, you pick an origin, you pick some axes, and let's call them this small x, well, let's call the manifold M, so there is no confusion. So this point is P, right? And now you have your coordinate system, which is going to be an R square of x and y, right? You will have a function, let's say x and y, that is going to give you a point in R2, right? And so again, you could say that x and y define the unit, so the unit is the map that you're giving me. Or you could say that the units are here and these are maps from a point to two values that have units. I do not know what is the advantage or disadvantage of doing that. But the point is that the maps are associated to this, that the units are associated to this. So now you could have a different set of units, and they could be r and theta. You have a different space here, right? And these are different units. And now if you have a map between this and this, you have something that transforms one unit to the other. Even more complicated, you could have two manifolds. Let's say, let's call this another manifold. Let's call it M. I don't know why. That's okay. And suppose now you have a map between these two things, right? Between the manifold. Now this itself will have its own set of coordinate, which is going to be, let's say, R3, right? And is going to have its own units, so let's call them A, B, C, right? And now you can make a map between this and this, and now you're going to have a units conversion between A, B, C and X, Y.
Could it not be said that even in the coordinate charts, it's not the points that have units, but because you still have to reference the origin when you translate. So even then, it's still the displacement has the units.
Oh
Would
yeah,
that
yeah,
be
yeah.
correct to
So
say? Yeah.
yeah, but you have to be careful, because the displacement because you think typically displacement as like a little line, a little vector. And since this is going to be in general a nonlinear transformation, talking about a displacement, it's a little bit fluffy. Because so suppose that I'm using r theta, right? So I have a point here, and right, I have a point, let's say here, and I have 2 points, right? If I am if I look at actually, let's do it even nicer, right? So if I imagine the 2 points here, right? If I am in in the polar coordinates, right, the radius is the same. It's the only the angle changes. So if you look at the chart in r theta, right, so this is r theta and this is x and y, the displacement will look like this. And which would correspond to this segment, like the curve. If you are in xy, you will think as your displacement as this. If you then have a differentiable manifolds and you look at the local coordinates, then things are fine, precisely because the differentiability at the point will preserve the linearity and therefore that will preserve the little segment. But as soon as you have something that it's not infinitesimal, you're going to have these issues.
I think also one more thing should be added that so of course the transformation can be nonlinear, but if we are trying to solve the problem just on the topological manifold, we should also allow for a transformation which might not even be differentiable, because that's one thing that is maybe missed off. Like after topological manifolds, people jump to differentiable manifolds, but when they say differentiable, they don't say is it one differentiable, twice differentiable, infinitely differentiable. All these are different levels where you might have problems. So let's say if you want just to solve the problem on topological manifold, you should have a solution which will not be destroyed by, for example, using transformation defined by this ugly Weierstrass function. If anyone has seen these functions which are everywhere continuous, nowhere differentiable, this is allowed in topological manifolds, but this would, destroy Jacobian. Like there is no Jacobian then. So then what you are left with is maybe working, redefining or rewriting this R2 space or Rn space locally such that, it might look like, something that has dimensions. So of course, if we have like any space, then and we can allow the arbitrary mixing, then we already have the problem. So when I saw your comment on Discord, I thought that maybe what one should do is one should maybe start with an abstract space which has no dimensions, and then introduce some linear map which would be like something like matrix, which would include the dimension in itself, and then would spit out something like a graded vector space. I don't know if you're familiar with graded vector spaces.
No,
No.
but keep in mind that we said before that a unit defines a measure. So let's do the simplest possible thing. Suppose that we have a one-dimensional manifold, right? Suppose that I have a map that is not differentiable, okay? I still need to be able to put, if I want to be able to define units, right? I need to have a measure here and a measure here. So this is mu1 and mu2. And I want to be able to not just transform the point, but I want to be able to transform the measure because, okay, fine, our measures are different, but I should be able to tell how my measure converts to yours. So while the function may not be continuous, it has to be at least measurable. Because if it's not measurable, then I define a unit and you define a unit and we can't convert our units. We can't convert our measures. So it is true that we should broaden the class of functions if we want to be proper to something that is non-continuous. But I don't think we can do something that is not measurable because otherwise it becomes a complete mess. So in the examples that you're giving, I don't know whether those are measurable transformations or not. Probably they are, because if they're not measurable, it's there. But
Yeah, so I think the Weierstrass function is everywhere continuous. So I think that answers the question. But maybe another comment, so I wanted to expand on, are these graded vector spaces. So it's basically a vector space which is simply a direct sum of smaller vector spaces. So let's say if I don't have Jacobian, I cannot transform the coordinates in a differentiable manner. I don't have a metric. Then really the only way I can separate the coordinates is that I declare that each coordinate has its own one-dimensional vector space. I define scalar multiplication and addition on each such vector space separately, and then I stack them up together into one vector space, which now does not transform as one. It does not take the one n-dimensional vector as such, but it takes its basically component by component, as long as it preserves that each component it's only added along that line. So maybe that could be helpful in thinking how to tackle the measures. And also what happens there is that you can, of course, if you start with these one-dimensional lines as their own vector spaces, but once you start considering let's say product spaces, let's say I have meter times second, that also defines a new vector space, which is now let's say graded by two numbers, for each dimension, and then you can start building measures or some analysis on that. If you use three physical dimensions, now you multiply, you now have this triple tensor product, and then you can at least start discussing about these things separately on each space, so there is no mixing, what is greater than what. But of course, when you have these isolated points, yeah, I guess there is some degeneracy that is bound to happen. But I think, already adding this measure, I think it's quite a jump. So I would maybe start, building this topology of, graded vector spaces, see what comes from that, because of that at least sounds to me like natural. Like I would not add seconds to kilograms because they just live in different worlds.
So there is also something called geometric measure theory, I think, where they do give, it does have a feel like this, where you have a measure for each, essentially dimensionality of the space. And they still, I think most of the time, they kind of live in some kind of Riemannian space where you can compare the the dimension, which is not general enough. But they do, like, the reason why that is useful is because not all the solutions that you need to some problems are going to have a differentiable solution. So for example, if you're looking for like films, right, and you're looking at this the side, how bubbles form up, right? So if you have two bubbles, then you will have the film that it's sort of these spheres, and then a flat thing in between, right? That this is like, imagine that these are two bubbles that are joining, right? And so so these are kind of like surfaces that are differentiable, but they connect to pieces. So the whole solution is not differentiable, and so to do these calculations and so on, you need something that it's a little bit more general, and that's why they have this geometric measure theory. So I do not know whether even pieces of geometric measure theory can be sort of recycled to do all of this. And again, we always have the problem that right now we're just thinking of manifolds, but what happens if these bubbles are in function spaces, so that each point is a function, what are the units there, and so on. I have no idea. So I'm not looking for solutions right now. I just saying what the problems are.
Yeah, so just to quickly finish my thought. So yeah, so one component I think was that for individual dimensions, I would start with building these isolated, individual vector spaces. But I think the second thing is that if we start constructing the space with dimensional objects already, I think this already gives us a chance to combine, angles, adding angles with distances, which is already a problem. So instead, I thought of maybe using a different structure that you use somewhere in your notes, this symplectic potential, something like that, because from that you get already this couple of conjugate momentum and the coordinate. So basically, you take something as a number, and then you produce it, quantities that are coupled also dimensionally. So then I thought that if we want something similar here, that we should start with again some abstract space which has no dimensions, and then when we define something like expansion in basis, then in this way we would introduce this, the coordinate and some object that absorbs the coordinates. So in the first case, it was this dx, which is the position or the coordinate, and conjugate momentum, which has the inverse of that. And I would expect that something similar should happen here. Otherwise, it will become a Frankenstein if we just, already start with coordinates. But that means that, there's this abstract space, which is like also what we do in manifolds, that we have these transition functions from one chart to the point on the manifold to another chart. But we always use these transition functions together, like sandwiched. We never work with the topological point itself. Yes. So I
Right.
think
So for that, I have something in the when we have differentiability, we can do cool things like this. These would be the maps. So that's as I say before, when you have maps that go from one manifold to the other, you are going to have maps on the coordinates that remove one unit and put another unit. And this is exactly what's going to map to the part of the tensor that are covariant and contravariant. So that sort of should come out. There is a question from the chat. What do you mean by a triple tensor? I don't know. Did I talk about triple tensor? Or you talked about
I mentioned that, yeah. So it's basically when we have the vector space, when we have these individual vector spaces coming from grading. So we have vector space, let's say, for kilogram, a vector space for meters, vector space for seconds. And now we want to imagine vector spaces that allow items or objects which have product dimension, let's say kilogram times second, kilogram times meter, etc. This would be vector spaces coming as products of these smaller vector spaces. So in this sense, that we create a vector space that is larger, but it is constructed on this, as a product of these lower dimensional graded vector spaces. And these tensor spaces then again are graded, but they're graded by all these doubles, triples of indices depending on what we consider. So it's in that sense.
Yeah. So looking at something like phase space, the problem is more complicated than that, because if I say that this is position and this is momentum, and then let's say that I have other two coordinates. Let's say that this is q1, this is q2, and this is p1, and this is p2, right? And if you imagine that now I boost, right? The new coordinates are going to be a linear combination of all these four things, right? So I'm going to have a new q1 hat that it's going to be a linear combination of these things with its own unit, and not all of these linear combinations can be spaces and so on. So you can't just start with, let's say, some fundamental things and build everything up, because the linear combination have to have the same status as the thing that you started from.
Yes, I agree. But on the other hand, if you say that there is a boost, well, it should be like, is the boost differentiable? Because if it's a differentiable boost, then now we can include the Jacobian, and Jacobian adds additional freedom to, let's say, move around the units. So it's like the boost, I think, is too simple. It's again, if you want, it's something horrible, take this Weierstrass or Minkowski question mark function. So then,
Sure.
so
You
what
can
I'm
do
saying
more
is that,
complicated things. Agreed. Yes.
yeah, so then the boost would be just yeah, I mean, it's a kind of a transformation matrix that would reshuffle the indices. So but this is already adding an additional structure. So that's why I'm trying to say something that applies to very basic thinking, and then when we start adding structure, we have this. That's why also let's say suggest that thinking about phase-space structure not as, let's say, fundamental, but also start at the skeleton and then see what else we add to it, because phase space is already including a lot of things together. It's not just dimensions. It's not just some transformation function. There are several things attached, and I want to trim them one by one. That's all.
Right, but the thing is going to be, again, the space exists first, and then you peel out some of dimensions and so on. So I can't construct the space in a way that I am building it from the 4 coordinates. Because if I'm building it from the 4 coordinates, I'm basically saying that those are more fundamental because I'm using them to define the space. But somebody else from a different frame will define the space in a different way. And so to them, those other 4 coordinates would be more fundamental. And then I don't have something that is relativistic.
But that's indeed the point. That's indeed the point, that if we don't have a differentiable coordinate transformation, then there is no fundamental choice of dimensions. You cannot compare them. You need at least some differentiability to allow comparing different charts and the mixing of the coordinates. If you don't have that, then every codomain of a coordinate chart will have its own, let's say, fundamental physical dimensions, and all of them will be correct because there is no way to compare if the mapping is not differentiable. So that's the point.
Yeah, but if I just have a kink, right? So if I am just not differentiable at one point, it's not a problem.
Yeah, so that's why I'm saying it's non-differentiable completely everywhere.
Oh, well, yes. Okay, fine, sure.
If it's just a single point, then yes, we have Jacobian opens hands, a lot, and that's already very helpful.
Yeah. So there might be so for example, if we don't have a Jacobian defined anywhere, sorry, we probably can't define the probability distributions in a way that we map from coordinate to the other. So there are going to be a lot of things that break, yes. All right, so this was just the manifold, and now we need the differentiable structure. Okay, and so let's do the simple thing that we basically, the main problem of the differentiable structure is that identified what are the correct physical objects, because if we don't do that first, we can't give them units. So for a simple case, imagine that this is time, looks like temperature, like this is time, and this is space. So let's call this x. And I have a trajectory, gamma, right? So this is a gamma of t, right? It takes a time and it gives me a point in space. Now this will have a chart. Let's say that this is in seconds. And here I also have a chart that it's, XYZ, come si chiamano? The Cartesian, let's say Cartesian. And so here I kind of have, now I don't know how to there's going to be a redundancy of notations here, but the maps are going to be X, Y, and Z. I'm going to have a map T, right? And so I can go then directly from the second to the meters, right? And I can write that. So this is the structure of the manifold. Then what you want to do is you're going to have sets of displacement in position, the space of displacement in time, right? And this basically is what the tangent space should be, like little changes. And now you can also have little changes in the coordinates themselves. And of course, you can map little changes of coordinates to little changes of, this is dsec. And you can map your little changes of coordinates to the little changes of time. And then you're going to have the d gamma here, which is your derivative, and this is where the velocity lies. The velocity is basically something that takes an infinitesimal differential in time and gives you an infinitesimal differential in space. So when you write this map in terms of this, now this map will have units of space over time. Right? Because now this thing is taking an infinitesimal change in seconds, and it's giving you an infinitesimal change in meters or angles or whatever you want. And this is the important identification that comes out of this, that does not quite match what people do in differential geometry, because they want to talk about tangent vectors as velocities, but in physics the velocity needs the time, right? A velocity is not just it's not just on a curve, but it's on a specific parametrization of the curve. This is where there is the main disconnect between the standard definition in differential geometry and and physics. That when you define a curve, you say, oh, I have a map from, let's say, 0, 1 to my manifold. And therefore, so let's say that this is my manifold, right? And this is my curve, right? Let's say that this is 0 and this is 1. The problem is that if I want to talk about velocity, I need to know that this has to be time. And if I make a non-linear transformation on that 0, 1, let's say, you take x squared, then you are changing the definitions and you are not going to have a velocity anymore, you have something else. And in physics, we typically differentiate between curve and trajectory, where the curve is just the locus of the point, regardless of what the parameterization is. And a trajectory, it's a curve with the specific parameterization, and the parameterization is given by time. And when we have the specific parameterization that is given by time, it makes sense to talk about velocity. And if we just have curves, it does not make sense to talk about velocity. And this is, again, another problem with all of this, is that the standard way to say whether a curve is differentiable is by saying that this map is differentiable. But I could make a change on the parameterization such that the map is not differentiable, but I haven't changed the points of the curve. So if I just say, this is my manifold and this is my curve, right? And I ask you, it's differentiable or not? Then the question is ill-posed, because you have to say, okay, with what parameterization? Because clearly with a linear parameterization is fine, but I could have a parameterization that has a kink, right? That has, that does something like this, and now here I'm not differentiable, and my curve is not differentiable. Or I can make a Weierstrass transformation everywhere, continuous, like the one that you were talking about, Julius. And I want to have a notion of differentiability that it's, I need a notion of differentiability that it's all in the space. right? I need to be able to say, well, this is my manifold, this is my curve. Oh yes, it is differentiable, it is not differentiable, regardless of how it is parameterized. And there is a way, and the simple way is this. So you pick a point, right? Pick a point P, and then you're going to pick two other points, and you're going to go closer and closer to P. And you look at the line, the segment that connects it. If the segment that connects sort of tends to the same segment regardless of how you are going to the points, then the line is differentiable, and what you tend to is just a tangent. If you have a line that is like this, you know, you could go to that point like this or like this, and so you don't always get to the same with the same vector. And so the idea of the ability of thinking about your line as made of just little segments, regardless of how you have divided the line, like how you make this linear approximation, it doesn't matter, because in the limit you get always the same line. That's essentially differentiability. So differentiability of a curve is exactly the property that I can take that curve, think it as a poly line, so a series of segments, and I take the limit and I get the curve. If I want to be able to think of a curve like that, it has to be differentiable. Because if it's not, at points where you're not differentiable, it's not clear how you're going to make the approximation around that point.
Sorry, but so suppose you have this polygonal line. Still, this is given in some, let's say, in some coordinate system, in some parametrization. If you start drawing lines, well, the straight line depends on where you're measuring. So it might be that it's differentiable in one picture, but when you transform, it becomes non-differentiable.
And
So
that's the cool thing, is that if the map between the coordinates is differentiable, then the thing is differentiable in all the possible coordinates. And that's what the differentiable structure is. The differentiable structure is we are all agreeing, not on a global linear structure, but we are all agreeing that this curve can be made of this little line. Then we're going to choose coordinates that are compatible with this differentiable structure, right? And now you really have a sense of what the differentiable structure is, right? You first say, these are the good lines. These are the ones that I can think of being made of infinitesimal segments. And then you find coordinates that are compatible to that. And so they're compatible with the differentiable structure. And then the change of coordinates is going to be differentiable.
So this, in some sense, already like presupposes that fundamentally the behavior is differentiable, and then we're just projecting it on different representation.
Yeah. So you're basically making this assumption. I will assume that all the geometrical objects that I'm studying can be thought as the limit of linear approximations, effectively. And the same is going to work for what's it called? Surfaces and all the other dimension, right? You kind of gonna approximate them as triangles, and then I think a triangle is the best shape, and then whatever that. I guess they're simplexes. I never thought about it. Yeah, you can make a local approximation with simplexes. That's and there was some other person that there is another guy. So anyway, there is a way to sort of do some type of exterior derivatives on these simplex complexes and so on. There was a person that a few months ago started to share some things, and we should pull him back. But anyway, that would be the idea, that all this differentiability comes from the ability or the assumption that you can do this.
Yeah. So simplices are for sure useful. I think there's even a theory of gravity called Regge calculus, which
Okay.
uses development by simplices. But yeah, of course, like you said, not how to say, not all these mathematical constructions are physical. For example, for people who study GR, they might have heard that for massive particles, the parameter is proper time that which they can measure on their watches, while for photons, for null geodesics, the parameter has no physical meaning, and actually what we're studying is equivalence classes. So what matters is the entire trajectory or like intersection with an observer. So it's like incidence relations, or like when you are considering like expansion or like distortion of images, then it's the ratio of these things that matter, not like the derivatives with respect to parameter. So of course there's also a physical process behind the parameter, and its meaning. So yeah, that is what also matters. Yeah, so that's regarding that. And the other thing, my question is, have you heard of Cartan frames? No.
I might have heard them, but I don't know what they are.
Yeah, so it is a different reformulation of, let's say, differential geometry or manifolds. It's that instead of taking as basis vectors the coordinate basis, one introduces this, let's say, abstract vectors, which then build their own like vector space. And then what one does, what one can do is one can expand these Cartan frames into coordinate basis. So what happens is that this Cartan frame, which is basically a vector with this Latin index, it becomes a two-index thing, which contracts with dx mu uppercase. Up. So this basically then, on one hand, it preserves this abstract linear space. On the other hand, it keeps track the mixing with the coordinates, and which is maybe a different way, like to state some similar idea that there should be some, let's say, abstract structure, abstract case that is working properly, and then everything else is a representation. And this Cartan frames, what they allow us to do is not only consider like Riemannian geometry, but it can also be used for projective geometry, can be also used for spinors, which are the fermions, like for that geometry, and many other geometries can be derived from that. So maybe it's just throwing out an idea that maybe for people to pick up, because I think it's quite a developed topic, and maybe it's one of these things that we just need to translate a dictionary, not to recreate everything from the ground up.
Right. So I right now for differential geometry specifically, for differential topology specifically, I basically would like to have something that doesn't do something completely different, but sort of clarifies some of these mismatches, and also extends notions to infinite dimensional vector spaces. Because that's the other problem that I have with differential topology in general, that these things only work with manifolds, and we need to do things in function spaces as well. So even if you're doing classical mechanics, whenever you are doing Lagrangian mechanics, you already have a differentiable calculus, like a calculus of variation. And the way that I would like to set this up is that these differentials are basically variations. And so I don't care that these spaces X and T are actually manifolds. What I care is that there are topological spaces that are locally isomorphic to a topological vector space. And then I can construct a tangent space, which is going to be the space of variations. And then everything that we're doing is going to work exactly the same, whether we are finite dimensional or infinite dimensional. Because again, I'd like to have one core set of tools that are essentially the same, and you work in classical mechanics, classical field theory, quantum mechanics, quantum field theory. It's always the same thing, because at the end of the day in physics we're kind of doing always the same thing. They're not so different. And I have for this I already have a good chunk done for defining these variation differential, how you want to call it. But that's kind of what it works. So going back to this, when we write, we want to be able to write dp equals dx alpha e alpha. Let's say I, dxi ei. Right? This is the typical thing that we want to write. And typically one interprets this as a vector basis. This is not the vector basis, these are here. These are the maps that takes a differential, a variation in the coordinates that have units to the variation in the space that does not have units. So these will have units of I, and these take a unit of I, right, because it's down, and give you something that does not have unit, right? So essentially this is a unit of 1 over I, right? So in, like I say, in as an example, you know, I have my dp, and then I have a dx that is going to be, you know, 1 meter, and I take ex. Actually, let's do it in polar coordinates, so it's more fun. So er, this is going to be 1 meter, and then I have d theta that, well, I don't know if it's 1 meter, but this is in meters. This is going to be e theta, and this is in radians, and this is no units. And effectively these things are partial p partial r and partial p partial theta. And this is the type of notation that was used in the 30s and the 20s when people were doing differential geometry. Like, it's not even something that I made up. This is how we were doing differential geometry. So a lot of things, if you go, you know, at the Einstein time, these are the things and now this makes sense, because you can imagine here, right, that the inverse is a p of x, y, z, right? It's a function that goes from the values of the coordinates that have units to the point which is not a unit. And so when you get, when you go to the differential, you're just making the differential of that map. And those are what we think of vector bases, but they're not bases because you can't sum them. Because if I have ER and E theta, I can't sum these two things because they take different units. So I can't just sum them as functions. And this basically gives you the general notion that if you have a big X, a big Y, right, and you have a map between these two, let's call this M, right, this dm is the tensor. So a tensor is a map from variation on one side to the variation on the other side. Actually, I should give it a direction. So M is right, it gives you a y. It's a map. Now let's do it with a. It's a map from x to y, right? And now I'm gonna have like a small tensor. Let's call it. I should have given it different a name. Let's call this n. Now this is a map from dx to dxy, to the space of variation. And if you're writing it in coordinate, and let's say that this is a 3-dimensional and this is 2-dimensional, then your n is going to have 3 indices down, I, j, k, and 2 indices up, lm, because it's getting a 3-dimensional variation and it's giving you back a 2-dimensional variation. And a vector, a velocity, is exactly like this. So a velocity is a special case where you have, again, time and space, and you have a map gamma that goes from t to x, and the velocity is just the thing that goes from dt to dx, and you write it as a vi, because you kind of would have a t underneath here, but since it's one, you don't write it, right? But really, it should be this. You have a v down there that contracts with your dt, and it gives you your dxi. I see then how the notation works by itself, right? This is like completely serious. So when you're gonna work with bigger tensors like the Riemann tensors and all that, you're basically doing the same thing. You're taking variation on one side and you give you back a variation on the other side.
Yeah, so just a small comment on this differential of P. This almost looks like a differential of a scalar expanded in Cartan frame vectors.
Sure. Of course.
It's because these vectors are also at the same time differential operators, like the basis of the coordinate, this d mu, they are also differential operators. So this ER, like if you just added one index and contract it with, it would be exactly the same thing. However, so that's why I'm suggesting, maybe, try to have a look at, Cartan frames or tetrite fields, how they work. But they also have this additional aspect, is that although with coordinates we can take second derivatives and they are mixing without a problem, if we are using Cartan frames, in general, the mixed derivative is not symmetric. There is this lack of commutation part, which is, in general, it should be there because coordinates and coordinate basis is very special. It's basically we can foliate the entire space with with surfaces, and this is very particular property. This is also
Yes.
coming from Frobenius theorem. If you don't satisfy that, basically meaning that if your vector fields are twisting, creating vortices, then you cannot have this anymore. And Cartan frames would have this component explicitly there. So I don't want to expand too much or harass, but I'm saying, have a look at Cartan frames. It looks very similar.
Yeah, but also, this is just the chain rule, right? Because we are really writing is dp equals a partial p partial r dr plus a partial p partial theta d theta. And now these are what typically you think as vectors, but they're just the maps.
So in Cartan frames, what would happen is that you have additional chain rule inside. So this Cartan frame acts on scalar as a differential operator, and then there is additional mixing matrix which connects the frame vector to the coordinate basis vector.
Right.
And this, yeah.
So, and I think something similar, like one of the things that I'd like to have from differential geometry side is a reinterpretation of so in differential geometry you have vector fields. And what I don't understand about vector fields is whether the parameterization that you use is significant or not. When you're doing a Lie derivative, right? Are you using, and Lie derivatives are going to be similar to what you're talking about. Okay, I have two vector fields. Well, if the vector fields come from coordinates, then but if they don't, they you can detect that. And the point is, what is it that geometrically I'm actually picking out when I'm making the derivative between Lie derivative between two vector fields? Is it dependent on the parameterization or not? Can we have one that depends on the parameterization? Because if I'm thinking about flows and I want to compare like Hamiltonian flows, that the parameterization is important because that parameterization is going to be timed and so on. But if I'm just comparing the foliation of curves, then I don't care about the parameterization. And so the vector field that I would get from the coordinates, and I want to study that, I don't want it to be depending on the parameterization itself because I just want to. So what pieces depend on what? this is a whole thing in differential topology, because we haven't even talked about geometry yet. All the things in differential topology that I haven't understood yet.
When you're asking about the Lie derivative depending on parameterization, are you talking about depending on the coordinate chart, or like a full vector field, or just like a line of vectors
So
parameterized?
you know, so what I don't understand, right? It's you know, you have a vector field, right?
Yeah.
And this is, in some sense, a sort of a map of derivations at each point. Yeah, it's going to be something like this, VII,
Hmm.
right?
Yeah.
And now I'm talking about this object as a derivation. Like if I put an f here, right, I would get some type of derivation with respect to some parameter.
Right. If
Right.
right, if one makes the association of vectors with derivative operators, which is obviously what is done in mathematics, but I don't think is necessarily implied that we have to for physics. Because even in mathematics, the definition of tangent vectors usually starts from equivalence classes of curves and what you were talking about of a curve being differential, and then it is shown that you can uniquely identify it.
Right, but the curve depends on the parameterization.
Yeah. But
Okay.
the equivalence class, you can, if you just have a curve, so like separate the terminology of curve and trajectory.
Yeah.
Then if you just have the curve, you can define a tangent vector. And then the trajectory, you define a velocity vector. Basically what I'm saying is a tangent vector and a velocity
Wait a
vector are
second. So
different.
let's say that I take this, like this line, I take a tangent vector.
Yeah.
Right? If I multiply this vector by a scalar,
Mm-hmm.
right, I will get something that goes faster. Okay, so if I have a right line, right? If I have just a line, my tangent vector will depend on how faster I'm going through the line.
Mm-hmm.
Okay, so it is not true that if I have this line, I will get one tangent vector. If I just give you the curve without parameterization.
Right.
So the tangent vector is picking up not just the direction, it's also is picking up the speed, the velocity of the parameterization.
Mm-hmm.
Okay, that's my problem.
Okay. Yeah.
So when I define things like this, I'm gonna have the same problem. If I rescale my alpha, I get a different vector field, even though the field lines are gonna be exactly the same.
So maybe I also thought about this, and I think here again it's important first to consider this, let's say, fundamental structure that we assume that we have. Like you mentioned, this differentiability we assume that we have, and then everything else is just projection on some representation. So here, I think what also could be useful is that first we start with this differentiable curve with some abstract parameter, and its reparameterization would not matter because it's just abstract, let's say, structure, a skeleton on which we'll start putting meat. But then when we have this mathematical machinery, then we can start, let's say, instantiate some physical process. Like I said, if we're considering trajectories of massive particles, of course, parameterization matters. And one of them, which is this proper time, gives you the time. So in this particular physical case, it matters. If we take null geodesics photons, then parameterization does not matter. So there are two different physical cases. Both of them are realizable, and for one it matters, for the other does not. But this is after we put this additional physical picture. I think beforehand we can very calmly use this abstract picture with abstract parameter, which we can scale however, and we know that without physics it has no other meaning. It's just structure that keeps pieces together. But what exactly happens to these pieces now is a physics question, not a mathematics question.
Yeah, but the point is that if the materialization doesn't matter physically, then the object that I'm studying should be independent on the parameterization.
So for null geodesics, that would be the case because the length is 0 for them. So parameterization does not change the length. So indeed, for them, it does not matter, but not for all physical problems. You need to define physical problem.
In the case where parameterization matter, I need to have a mathematical object that depends on the parameterization.
Yes, and so then you can, this, let's say we have this abstract parameter, and then we want to transform to this proper time. So this is not just an arbitrary rule that we can assign. This proper time, it simplifies the equation in some sense. It basically kills off this, square root of the length. So this is very particular choice of parameterization. Any other case is, is as possible as, as mine or yours. So I think abstractly, it's for sure it should not matter, but it's when we put the physics, then it will matter. But we need to have the physical problem.
As I said, there are two things. One, I just have x, right? And then I have a curve because I'm just moving, I just have a locus of points in x, and that does not depend on the parameterization. And then I have something where I have a t, I have a time, and I have a gamma, and now the parameterization matters because I'm going from points that are here. And so the parameterization is just a representation of those points. So if I change how I'm representing my points, I'm gonna have to change the curve because it's a different thing. Right? So my problem is that I don't have these two separate things fleshed out in differential geometry as two separate objects that it's clear that one depends on the parameterization and one does not. I have something that it's a little bit in between and I don't understand what depends on the parameterization and what does.
So for this example with time and x, I think here the problem is that we're already using physical dimensions. So here my proposition would be to draw an additional mapping from abstract parameter to abstract position along the integral line of this abstract frame vector. So then there is no physical dimension, there is no physics attached yet. It's only when we map parameterization to some choice of time ordering, some how to say parameterization of the position along the integral of the curve of the vector as the position in meters. That's when we have this importance. But to draw an abstract line, abstract curve, that should not be a problem. I mean, it's just an abstract concept, like differentiability is an abstract concept. It's only after projection we have this, we can answer the question if it matters or not.
Again, I have two cases and I have to differentiate those two cases. I don't understand what it means to attach. No, I have the case where I just have a curve, parameterization does not matter. All the physical things that I define on that curve should not depend on parameterization. And then I have another case in which the parameterization is matter. Look, I don't have units yet here. Like there are no units.
You have time and x. You have
No,
time and
these
position.
are manifolds. These are just the manifolds. The units are on the coordinates.
Yeah, but how do you measure? Like, what is the manifold of time?
It's just something that it's isomorphic to R. I haven't chosen a set of units.
Okay, so then it's like real line. So then it's okay. So then it's basically the abstract case that I told you. So then to convert to physics, you need to convert first from the abstract vectors or abstract basis to the coordinate basis, and then you need to convert from abstract parameterization to physical parameterization. So there are two.
This is not an abstract. This manifold represents the instance in time.
Yeah, but in what units? Time, seconds. We have not.
Instants in time are things
but
that
these are different. Time second is different from a year, different from like an hour. It's a different. Each of them are different.
The instance in time do not care how I label them.
Yes, but when you take a segment of parameter, then
if I want to define a parameter, I will get, if I want a number from 0 to 1, if I want to write gamma as 0 to 1, yes, I'm picking the unit. But if I say gamma, let's say this is gamma of t as the manifold of the instance in time, I'm not picking a unit.
Okay, so as a mapping, yeah, I see that point. But when we have mappings between segments, then there is a parameterization. So I think maybe it's again notational issue, not the conceptual.
I will have a map that goes, let's say a map T from R to T, right? So this is my coordinate and this is my manifold. And then I'm gonna be able to write, from R, my gamma, like I effectively write gamma as a T, right, of some number that I call little r, right? And now I've written um, my curve, my trajectory in terms of a specific, let's call it seconds, right? Let's say like this, seconds. And then I will have a second. And then I put here my little number. And now my function is a function of a number.
Yeah, so I think it should not depend on R, but as on the function of R, it will depend.
Yeah, this is this. Like the second is going to tell me which units I'm going to use. And again, the point is that I'm trying to do all of this in a way that it maps as best as it can to the tools that are already there in manifold and differential geometry, right? This is just a coordinate. So when I pick a coordinate, when I have a unit, and when I pick a point in the manifold, those are the positions in space, so the instants in time, right? Those are like unitless quantities. And but the map, the real map, right, is defined on those instants and positions.
So maybe one more small comment to mention. We are talking about units and dimension, physical units, but there can be units which have no physical dimension. It's just like unit of a real line. So there is also how to say, we intrinsically, or like without saying, we are assuming that 1 unit of a second is 1 unit of the abstract parameter, and they don't have to be the same. We can take one unit of a real number line, which will correspond to 10 seconds or 100 hours, etc. So there's additional like mapping involved, or like scaling. And
I
yeah.
mean, the issue isn't that the units necessarily correspond to something physically. The issue is the typed nature of it. Because when we introduce, physical dimensions, what we're doing is we're typing quantities by some other variable, like its dimension, and then identifying selecting an identity in that space will select a identity element or a unit. Sorry. In any case, though, even if you pick a unit or a dimension that does not correspond to something physically, you're still typing quantities by something that will then mess with everything else you do in the same way an actual physical unit would. Because even if you choose, units of the real line, okay, but you can only add two elements that are both units of the real line. You can't add something that's units of the complex plane. You get all the same issues just from the fact that everything's typed now, regardless of whether or not it corresponds to something in the physical world.
Yeah, so my point is just that this abstract picture with abstract integral lines of vectors, vector fields, and abstract parameterization is just, let's say, the reference point from which, by chain rule or by choosing to a different, moving to a different basis, we can move to a physical picture. And the question was that where can we store this, differentiability, or like, stuff like that. And my idea is just to push the differentiability and nice properties to the abstract picture. And once we have that, then we can introduce the physical units, and then we can ask the question, what is physical, what is not. This purely abstract picture is just to contain the nicely behaving geometry, or that's all. That's all that I'm thinking about. Everything else is no, it's a different problem, but that's not why I prefer this abstract picture first, and then moving to a different frame.
Yeah, and I mean that's fair enough. I look at it the same way. The only point I was making of the abstract units and physical units will behave the exact same way as far as the mathematics are concerned.
And my point is that I need to be able to keep track when things depend on the parameterization and not. Right now, I can't, I don't know how to do it in the context of differential geometry. I don't think it can be done, but if somebody comes and says, "Oh yes, this is how you do it," perfectly fine. I'll stop, being critical. Okay, so it's already 12:30. We didn't do Riemannian and symplectic geometry, but I think we stopped. To me, Logan, do you understand better the problems that I had?
Yeah, because like we said before we started this, if there isn't anything on the AOP website specifically about this problem, so having a full talk about requirements is definitely helpful. Yeah.
Yeah, and I can put in the Discord server the links to the piece. In fact, let me do it 1 second right now. So I can stop share this guy. Can I stop sharing this guy, or it's gonna be impossible? Stop share. There we go. And now I can share on this side just to give you a sense. Because I never cleaned up these pieces, and these could also go in a. So I had this document that it's the thing about the informational granularity and this fineness of statements and so on. And here I had, so the main insight there was that, you know, with the topology, we can say that the position of the object is between 0 and 1 meter is narrower than the position of the object is between 0 and 1 kilometers, because this set is contained in the other set. So you can compare size with topology only if things are fully contained in one another. And what you need here instead is being able to say that between 0 and 1 meter is smaller, is finer than the position is between 2 and 3 kilometers. So this gives you more information than this statement. Right, so that would basically what the granularity thing would be. It tells you, oh, yes, if I knew this, if this is true, I know a lot more information on the other. And the insight is both geometry, probability, and information theory are the same thing, right? If something is smaller than a region is smaller than another region, it's because if I tell you something is in that region, it's a lot more information than if I told you that the other thing is in the other region. So there is this insight that all these geometric, information theoretic, probabilistic things, they're all related to each other. And so the idea is we need to define this thing, and I did have some, idea of the current attempt. You define this binary relationship, and then you can find lots of properties just effectively by saying that you have this offset monotonicity property, that it's something that again I cleaned up and recovered from other work, and I could do some things, prove some things, but never get to the whole way out and whatever. Then the other part is the definition of differentiability, of essentially defining a differential as sequences of vectors that in the limit go to a particular vector. So you define what I call a convergence envelope, which is just a sequence of scalar that go to zero. And then you can define a differential as something where for that particular sequence things go to a t, and now that t is basically the tangent vector of the sequence, and then I can define the derivatives and show that the derivative have to be linear. I can define chain rules. So there's a lot of stuff that here already works. There are details that I've never figured out exactly, that now I have a much better sense. So I didn't use the fact that the vector space has to be locally convex. And I know that whenever people define relational calculus, they want a locally convex topological vector space. And I didn't understand, like my definition seems to work without requiring that. And the point is that, yes, they work, but if you don't have a locally convex vector space, your derivative exists, but there might always be zero. So they tell you absolutely nothing about the curves because there are no linear functionals. And so there are all these pieces that could be cleaned up, but this is basically the theory that I would like to create for having a tangent space that not only recovers manifolds, because I can recover somewhere here the Frechet derivative. Let's see. La 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 la. Yes, DMT to be normal vector spaces, and the notion of Frechet derivative and the new derivative coincide, right? So I recover the Frechet derivative, and I recover even some other derivatives that are used in differentiable calculus. It's calculus of variation, not differential, calculus of variation. So it's very similar to what something exists, except that there are some clever bits that makes it better behaved. That's basically it. But again, this has never been cleaned up. I was something that I do it kind of for fun, and then the goal would be to work this up and make it work. So basically, I'd like to have one derivative for everything, right? I would like to show that the exterior derivative, it's this derivative when you're taking the proper multi-vector spaces and you're doing this, right? But that would be the holy grail of all of this, so that we can work. So my goal would be to exactly have the same definitions that work both for manifolds and for functional spaces. Because on the other side, I'm trying to tame function spaces to work better than Hilbert spaces. I need to find vector spaces that work better than Hilbert spaces for quantum mechanics. And there are sort of some of the issues. Like it's very similar issues, and I think that at the end of the day, it's always the same one issue once you figuring out what is the correct place to look at, and yeah, I'll put this stuff on Discord so that if you want to peruse, but regardless of all this, even if we just say, okay, let's just concentrate on manifold, let's clean up what depends on parameterization, what doesn't. So that we can have a good understanding of what the lead derivative is, that would be already fantastic for me, because it sets me up to understand better, let's say, connections and all the other things that you have in Riemannian geometry that we haven't talked about. Because at the end of the day, a lot of those things are lead derivative in disguise. So I don't know if it makes sense, any of the things that I just said.
Yeah, completely. I'm just thinking sometimes how much of sense can we extract just by considering the abstract properties, and how much it really depends on the physical scenario. Like if we choose particular potential or something, and does it mean that how sure are we that we're not building a Frankenstein instead of a nicely behaving theory?
Like the way that I approach it is, I want to have crystal clear what are the assumptions that go in on the mathematical tool. Like when we and this is the thing that I currently don't have with differential geometry, right? So if I start having a notion of curve and trajectory that are distinct, and then we have a notion, we understand what the notion of a lead derivative gives me, like does it depend on the parameterization or not, and so on. Then once we have the physics, we can say, oh, in this case, I need this tool. This is the piece that right now we don't have in physics. We go around like headless chicken, just taking some random tools and putting them in and see what happens. No, we have to understand this is the physics problem that we have. This is the specification of the physics problem. Therefore, this is the correct tool to use. And it can be done. And it has to be done like that.
Yeah, I remember one instance when I was thinking about Schwarz spaces and how everyone is talking about faster than polynomial decay. But then I also thought that, okay, it's almost always given in Cartesian coordinates. If you switch to different coordinates, let's say polar, and you have the angle now as a compact coordinate, so it has finite range. It might be that we don't even need any decay in in that coordinate, along that coordinate, and that you cannot see by just studying Schwartz spaces individually. You need geometry on top of that, so that kills a bit of this Frankenstein features.
So I can show you how I solved that problem 2 weeks ago, and then probably we should stop. But let me do this, because that was the problem that I had. Like when I say, okay, Hilbert spaces don't work. Schwartz spaces are better behaved, but I don't have a physical justification of why should I have Schwartz spaces. And so this is the write-up of what the problems are for Schwartz spaces, that you don't have that small state changes lead to small changes in measurable quantities, and this is something that you want to have. Like if you don't have this physically, it just does not make sense. Measurable quantities have to be well defined in all frames. It can't have that quantities defined for one frame, like position is defined for me, but it's not defined for you. That doesn't make any sense. I have infinite variance in my position, but you have finite variance for your position. Those things do not make sense. And again, Hilbert spaces do not satisfy this. And then you also want that different physical systems have a different mathematical representation. So if I give you the state space for one particle and the state space for a billion particle, it can't be that they are the same space. It makes no sense. And quantum mechanics on Hilbert space is inconsistent with these three requirements. So what I want is something that works better. So the way that I have it right now is I have these tentative things that satisfy those things. So those three things, at least those three things are fixed. And the way that you fix them is that you have a vector space, which is a complete second countable complex topological vector space. And we need a complex vector space because otherwise you can't do quantum mechanics. It needs to be topological because I need to know what the limits are. It needs to be second countable because if it's not second countable, I can't physically explore that space because I would need effectively more than countably many experiments to go and know what the state is, which I can't do. And complete just means that if I have a limit that respects everything good, then that is also a state. So if all the limits converge, then the thing is a state, which is what you also have in a Hilbert space. So the problem of the Hilbert space is that the topology is generated by the inner product. That's the problem, that's the whole thing that kills it. So V is also equipped with an inner product, and an observable is a continuous everywhere defined self-adjoint operator, meaning that it's everywhere defined, all the states must have the value defined, and it needs to be continuous because small changes in states have to give you a small change in the observable. So this is completely physically justifiable. Then V is equipped with a set of defining observables with a well-defined Lie algebra of commutation relationship. This is how we define spaces anywhere. We don't just, when we say, oh, I have a qubit. What does it mean that you have a qubit? Well, that you have this spin 1/2 with a particular commutation relationship. So this is something that we do in physics anyway. Just put in the definition. And then you say that the topology is the coarsest vector space topology, making the defining observables and the inner product continuous. Which makes sense. The probability have to be continuous, and these things have to be continuous. Now, the trick of all of this is that once you say, let's say that position is continuous, then position square is continuous because you're combining two continuous maps. And also x to the n has to be continuous because they're all continuous. Same thing, p is continuous, then p to the n is continuous. And therefore, every monomial of x and p have to be continuous. What you can prove from this axiom that the topology is the one generated by this type of semi-norms, where you're just taking the square root of the expectation of the elements in the unital algebra, which is going to be all the monomials of position and momentum, for position and momentum. This gives you exactly the Schwartz topology if you say, oh, I have position and momentum, and they have the standard commutation relationship. So I don't solve the problem by saying, oh, in this particular case, no, I solve a problem by giving some definition that you must have physically, because otherwise you have junk, and then find the clever little bit of math that pulls the whole thing and makes it work. And the cool thing is that the proof of the topology, oh geez, it's so short. Look at that. It's not even half a page, because it's the most obvious thing that you would like to have, both on the math side and on the physics side. And it just works. So this does not solve everything, of course. There are still open problems. So for example, I need a sense that these defining observables define the full space. There is nothing extra that I have other operators. I don't have that yet. I don't have this notion of completeness. And I also don't know how to define the ensemble, the space of ensembles, because I do not know how to define a trace right now, because since I'm renouncing to the Hilbert space, I have other pieces that I need to get in some other way. Right? But I'm pretty sure the physics works, so it has to have a corresponding mathematical definition that it's simple and it's gonna work. And the way that you make this works is to find 10, 20 possible different candidates of mathematical definitions, and find the one or two that works the best, and that gives you proofs that are short. You know that you have the right definition when the proofs are short, right? So this is the piece that I'm saying I'm doing right now for quantum mechanics, because, but ideally, all of the math that we have in physics should be like that, should be with definition that we can justify from the physics. This is sort of a piece that I have right now just to show that these three conditions are satisfied, that this definition works. Therefore, I know that these pieces are good. I don't have all the pieces, but I know that these pieces are good. So that's how I get to Schwartz spaces, not because I say I want Schwartz spaces, but because I want my operators to be continuous, and I want a Lie algebra that fully characterizes the space. And this is the cool thing. If I just told you Schwartz space, if I get the Schwartz space on Rn, and I get the Schwartz space or Rm, the Schwartz spaces are isomorphisms as vector spaces, as topological vector spaces. So if you only have the Schwartz space structure, you wouldn't be able to distinguish whether you have 1 degree of freedom or a billion degree of freedom. So the state space for a particle and the state space for the whole universe would be equivalent, which of course makes no sense. But since I added the Lie algebra, yes, you can make the linear transformation that goes from one space to the other, but they are not going to preserve the Lie algebra, because the algebra has finitely many generators, and once I have a linear transformation, that Lie algebra will have to be mapped to generators that are exactly the same number. Okay, they can't change. And so I can distinguish, because I've added in the definition the Lie algebra, I can distinguish between one particle and a billion particle. But did I do something weird? No, I just added in the definition everything that in physics we do anyway, which is define the observable with the commutation relationship. So you see, the physics can guide me to figure out what is the correct mathematical condition. It took me like 9 months, right, to figure that out. At the end of the day, it was obvious and simple, but God, to find things that are obvious and things that it takes a lot of time. So now you guys can help me figure out all the other stuff that I need. Okay, so this went a lot longer than I expected, so I think I should go and prepare lunch. And I don't have a topic for next week, but we can discuss in Discord. And thank you for the people that are still here and hearing me rambling. And we'll see you next time. Bye. There we go.